For this video, we are going to prove that the limit of a sequence 1 over n squared as n approaches to infinity is equal to 0. This is still part of videos related to review on sequences and series, essential for us to understand topics on real analysis. And for this video, as a disclaimer, what we're going to do here is to use the definition of a limit of a sequence. It is stated that the limit of a sequence exists or it converges to a certain number if for every epsilon greater than 0, there exists a natural number k such that for all n greater than said k, the terms in our sequence satisfy this form. Per definition, it should satisfy the sequence minus the limit itself is less than epsilon. So our goal is to come up with a proof that will actually provide us ideas that this is true. And how do we do that? Before we will start with our proof, let us try to come up with our scratch form here, or just scribbles of what would be our target, because it will guide us later on as to how do we apply necessary algebraic operations or properties in our proof. So our limit, or sequence here is 1 over n squared. And x, the limit itself is 0 because x is the limit, x sub n is our sequence, less than epsilon, which gives us the absolute value of 1 over n squared less than epsilon, or simply the positive of 1 over n squared is less than epsilon. If we could establish this portion, and that means we're able to emphasize that our limit for our sequence 1 over n squared is really 0, or is converging really to 0. Since part of the proof will involve epsilon and of course other values, we can restructure this further. Again, part of our scratch is if we are going to cross multiply or multiply both sides by n squared over epsilon. So you will have here 1 over epsilon is less than n squared, which will give us, let me change the color of my pen, which will give us 1 over square root of epsilon is less than n. Again, if we could establish this, then that relates to here, and then later on again, we have established that proof using the definition. So, so take note of this because we will be maybe arriving to that later. So going back here, going back to this color, so let us have here the proof. By our definition, we are going to introduce a certain small value epsilon. So let us have, let epsilon be greater than 0. No matter how small, it's greater than 0 here. In the previous video on the sequence 1 over n, we're able to invoke the Archimedean property because that's really applicable to that. But here, let us also take another method or another step, as we are going to define or introduce a certain k, because that's part of a definition. There exists for every epsilon greater than 0, there exists a natural number k. Okay, so let's define this using the identity that we have applied here. This one. Okay, you can't see that because my pen is white, but 1 over epsilon. Define k 1 over the square root of epsilon, element of real number. So this fits the definition. Okay, now next part of the definition should be then n is greater than or equal to k, but k should be a natural number per definition, and k in this case is 1 over square root of epsilon, may not be a natural number. Hence, let's not equate this to k, but just simply greater than k, which is again 1 over square root of epsilon, which implies further, okay, that you have here now that n is greater than 1 over square root of epsilon. As you can see, it is already going to this form here, but of course we just need to complete this, and we are now assured that it will really go to what is intended because we were able to come up with this form here. But let's simply continue because the proof should be complete. Okay, so let's complete here. Thus, looking into that, you have n squared is greater than 1 over epsilon. Or we can take the reciprocal of both, and we need that because our sequence is 1 over n squared. So 1 over n squared, and the reciprocal of 1 over epsilon is epsilon, and the inequality symbol will be interchanged. Okay, so we now reach into this, so you simply need to complete here. Hence, for n is greater than k, we have changes to black. Okay, the absolute value of 1 over n squared minus 0, which is equal to 1 over n squared, is less than epsilon. Okay, so cutting the middleman here, which means 1 over n squared minus 0 is less than epsilon. Again, take note, that is the definition, the last part of the intended part of the definition. Hence, we can now declare, therefore, the limit of 1 over n squared as n approaches to infinity is equal to 0. This ends our proof for this given, the limit of the given sequence. So again, we were able to start with this scratch portion here for us to be guided on what are the possible outcomes that will assure us that we are on the right track. Then we now introduce certain epsilon greater than 0 and use the value here, or assumed value for our k. Take note, k here is not necessarily a natural number, that's why we don't have the equality here. And then we apply reciprocation, and finally we arrive to this. Thank you very much for watching.